Welcome to this video about the expanding universe, and in this video we're looking at the Doppler effect. This is part of the higher physics course and the R dynamics universe topic. So these are the things that we'll be looking at: what the Doppler effect is, the expression for it, and how the frequency changes when we've got a stationary observer or a moving observer. So you will, even if you're not aware of it, have experienced the Doppler effect many times. The most noticeable is when you have a police or an ambulance or a fire engine coming towards you or moving away from you that has its siren on, and you can hear a change in pitch as it comes towards you and as it goes away from you. Equally, if you've been at any motor racing events, that will be the same. Or somebody's driven past you within a noisy car, when you can hear a change in the pitch of it as well. So as they come towards you, the pitch increases. As they go away from you, the pitch decreases. If you were doing an impression of a motor racing car, you might even go meow, and that's really showing the effect. The meow is coming towards you and the meow is going away from you. And the pitch from the engine is actually the same, even though it sounds like they might have been changing gear to lower the pitch. That's not actually true. So you can see the fire engine sound in this video here. So as the siren is coming towards you, there's an increase in the wavelength, or an apparent increase in the wavelength, and as it goes away from you, there's an apparent decrease in the wavelength. We're going to explore exactly what's happened in a bit more detail just now. So the Doppler effect in general is the change in the observed frequency of a wave when a source or the observer is moving, because it could either be the source of the sound, like the ambulance or the fire engine, or it could be that you are moving towards a stationary source of sound. We're going to focus on the moving sources and a stationary observer. So if we throw a pebble into a pond, then we get a series of ripples, and wave fronts of a particular frequency are produced and move outwards from the center of the source. The difference between the wave fronts, that's basically the peaks of the waves, is the wavelength. And all observers, no matter where you are, would see the same wavelength no matter what the position is. So you see the same ripples moving across the pond, whether you were standing on one side of where the stone went in or the other side of where the stone went in. If the source is moving, however, then there are more wave fronts per second for the source moving to the right than there are to the left. So the wave fronts are bunching up closer together, and so you hear an apparent higher frequency. And behind, there are fewer wave fronts per second, and they're further apart, so this results in the change in frequency as the object moves away from you. So if the source of the sound, the waves, is moving to the right here, we get the wavefronts, more wavefronts per second to the right in the direction that it's moving. The waves are bunching up together, and we get less wavefronts per second on the left of it as it moves away from it. So we have a relationship that we can derive, but we're just going to show you what it is for the frequency of the observer, and that's the speed of sound divided by the speed of sound minus the speed of the source, Vs, multiplied by the frequency of the source, Fs. So the observer frequency is F 0 or F0 or FO, and the frequency of the sound is Fs. If it's moving away, then as it moves away, the frequency is decreasing. So we have the same relationship, except the terms at the bottom here are added up together rather than taken away. So you will need to remember whether it is a plus or a minus that you need to put into the relationship. And that depends entirely on whether it's moving towards you or whether it's moving away from you. So if you can in your head think about what happens to the sounds that go meow. So it's decreasing as it's moving away. So to get a decrease in the observed frequency, we need to be dividing by a bigger number, and therefore we've got the adding at the bottom of the relationship. If it's coming towards you, meow, meow. So it's coming towards you, the first part, then it's a higher frequency that we hear because the wavefronts, more wavefronts per second are reaching you. So that means that we're going to have a negative at the bottom here. So the relationship on the datasheet is as shown on the screen here, and you do have to remember which one, whether it's the plus or the minus that you're going to use, depending on whether the object is moving towards you, the source of sound moving towards you or away from you. So let's look at a particular example. We've got a student standing on the platform and a train is approaching, and it sounds its horn as it comes through the station, and the train going through the station is moving at 25 meters per second, and the horn has a frequency of 200 hertz. And we're asked to calculate the frequency that the student hears as the train is approaching the student, and the frequency that the student hears as the train is moving away from the student. So we need to consider the relationship of this 200 hertz frequency, and we need to say what's coming towards us. So if it's coming towards us, it's increasing in pitch, and therefore we're going to have the negative sign at the bottom for our relationship. And then we substitute in the speed of sound, and we take away at the bottom there the 25 from 340, and we find that the sound that they hear coming towards them at that particular speed is 216 hertz. We do similarly when it's moving away. This time we've got to remember that we've got the plus at the bottom of the relationship sheet, and we end up with 186 hertz of frequency. Okay, it's worth noting that the change isn't the same. Even though the speed has been the same coming towards and moving away, it went up from 200 to 216, and it went down from 200 to 186. So there's not the same change. So you can't just work out one and then say, oh, it'd be the same increase or decrease in the other direction. That's not true. Okay, so here's our second example here. So we've got a train emitting this time a frequency of 800 hertz. And we have to describe the frequency of the sound as heard from the person as it changes, and explain in terms of the wavefronts why this frequency changes. And we're given a frequency of 760 hertz that is heard, and we've got to work out the speed of the train relative to the person on the platform. So we're asked here to describe how the frequency of the sound heard by the person changes as the train passes through the station. So presuming that the sound is being made as it's approaching the station to warn the people standing on the platform, then the frequency of the sound would increase as the train comes towards the person, and then the frequency of the sound would decrease once the train has passed the person. If we're going to explain this in terms of wavefronts, why this frequency changes, we could make a diagram, or we could describe in words. So the wavefronts are closer together as they approach the person, and then they're further apart as they pass the person. And you can see this in the picture at the bottom there, showing the wavefronts being closer together as the train's coming towards and further apart when the train's gone past. So we were finally told that they hear a sound of 760 Hertz and the train emitted 800 Hertz frequency. So we can work out what's happened here. So the frequency is lower than it happened to be, so it's moving away. So that means we've got the relationship F equals Fs times V over V plus Vs. So we've got the plus at the bottom because the frequency is decreased. Then we can substitute in our values, including the speed of sound, and then we're going to solve it. Okay, this is a bit more complicated because you've got to multiply out the particular terms. So remember, always do the substitution before you do any rearranging, because that will ensure that you have the maximum parts correct. And what we find is that the train is moving at 18 meters per second. The Doppler effect has a number of different applications. One of this is the police radar gun. So the police will send out radar towards the car, and because the car is moving, it'll be reflected off there, and they'll be reflected at a higher frequency. And by measuring the frequency of the reflected waves, we can work out the speed of the car that was coming towards us here. Okay, this isn't something that you'd be able to need to describe as part of the higher physics course, but it is something that is worthwhile being aware of. So this is slightly different in the terms that the source of the sound, the source of the waves is stationary, and the police car, and the car coming towards it that's being measured is moving. Another use would be Doppler ultrasound. So when you have a unborn baby scan of a fetus, they check the growth and the structures, but it can also be used to check the heart and the blood flow. And so the ultrasound is continuous ultrasound used, and it pulses in and it reflects off, and because of the movement you can work out how the frequencies change, and then you can work out the speed of the movement, and you usually hear that as a tone. So if you listen to some videos on ultrasound, you'll be able to hear the kind of whooshing noise that is displayed to give you an idea of the heartbeat. Okay, so what we looked at in this video is we've looked at what the Doppler effect is, and we've looked at the relationship for that and done some calculations for those, in particular where we've got a moving source coming towards us or moving away from us.